In this lecture, I'm going to discuss about induction motors or AC motors. Um, if you remember the breakdown of or the types of electric motors, mainly DC motors and AC motors. So under AC motors, we have induction motors and synchronous motors. Induction motor is asynchronous, that is why the other one is called synchronous motor. And under induction motor we have to discuss about single phase and three phase motors. So in this video lecture I'm going to give you an introduction to three phase induction motors. So AC machines are typically preferred to DC machines mainly because of the availability of alternating current as a commercial power supply, and also AC motors are generally more robust and less expensive than DC motors. That means the maintenance is more easy, and they normally don't get faulty soon, and also cost, the construction manufacturing wise, it is more easier than DC machines. Therefore AC machines are very popular. So there are two types of AC machines. One is induction machine and the other one is synchronous machines. So AC machines work on the principle of rotating magnetic field. So when we say rotating magnetic field, um, in case of DC motors, DC machines, you saw that we have a steady magnetic field, and the rotor is rotating, but the current in the rotor is actually alternating current. But here the story is completely different, where in AC machines we have a rotating magnetic field. The induction machine or asynchronous machine can be used as a motor and as a generator as well. However, it is most frequently used as a motor. So induction motors are the most common and frequently encountered machines in the industry. Induction generators are seldom used. Their typical application is in wind energy conversions. So in wind energy conversion we use induction generators. Otherwise mainly we use induction machine as a motor. So induction motors have number of advantages. They are simple and robust construction, low manufacturing cost, low maintenance, run at constant speed from no load to full load, not like DC machines, and they are directly connected to an AC power, and speed depends on the supply frequency. Therefore, if you want to change the speed, you have to change the frequency of the supply, right? A wide variety of induction motors are available for a range of applications. The most popular induction motors are wound rotor and squirrel cage rotor induction machines. However, the majority of induction machines are used in industry are squirrel cage induction machines. You will know what is meant by wound machine and squirrel cage machine in my next few slides. Induction motors exist in single phase and three phase both, right? So both single and three phase induction motors are widely used. So single phase induction machines are most frequently used in household appliances such as washing machines, refrigerators, food mixers and blenders, handles. Every home appliance is basically using a single phase induction motor, induction machines, because normally for domestic use we use single phase only. And three-phase induction machines are used in the industrial applications such as pumps, fans, compressors, paper mills, in which you need very high power. We have to use three-phase. Some of the examples are shown in the next slide, where we use industrial machines, induction machines. And similar to the DC machines, in AC machines we have two parts mainly. Stationary part is called the stator, revolving part is called the rotor. The rotor is separated from the stator by a small air gap, maybe 0.4 millimeter to 4 millimeter air gap. The gap changes according to the power of the motor. For high power motors, the gap might be larger. So stator, if we look at the stator now, it is again consists of steel frame that supports a cylindrical core made up of stacked laminations. Again, it is laminated core. You know the reason is to reduce the eddy current losses. A number of evenly spaced slots punch on the laminations provide space for the stator windings. The stator winding consists of three individual windings which overlap one another and are offset by an electrical angle of 120 degrees. This is electrical angle 120 degrees. As you remember, the three-phase supply, the electrical angle between each phase is 120 degrees. So here in the stator, it has three individual windings which overlap one another and are offset by an electrical angle of 120 degrees. And if you look at the rotor, the rotor is also composed of punch laminations to accommodate the rotor windings. There are two types of rotor windings. First one is conventional three-phase windings made of insulated wire, and other one is squirrel cage windings. So these types of windings gives rise to two main classes of induction motors: wound rotor and squirrel cage. So they are classified according to the construction of the rotor. So let's first look at the squirrel cage rotor. You know, you might have seen squirrel cages. So this looks like same, the functional wise. So as well, and the appearance wise is like a squirrel cage. The cage is constructed from rotor bars, generally copper. Sometimes it is used, aluminium is used to construct the rotor bars, but copper is better because its conductivity is higher. Insulated and embedded in the rotor slots, and shorted at both ends by end rings. So at the both ends you have end rings. So this is inside this. Here you can see the rotor, squirrel cage rotor, and here you can see the copper conductors and these conductors are short circuited through this end ring, and on the bottom as well these bars are connected, so actually they are short circuited. Then if you look at the wound rotor or slip ring machines, the wound rotor windings has the same form as the stator winding and rotor winding. So it is a winding, but in the squirrel cage there are no windings. The windings are connected in star. In the rotor, the windings are connected in star. The terminals are connected to 3 slip rings. So these are the 3 slip rings, like commutator in DC machines. So this is called the wound rotor induction machine. So the physical construction would look like this. Here you see the slip rings, 3 slip rings to supply the rotor with 3-phase current. And here you have to use brushes. And exploded view of slip ring motor. Again, this is the rotor, wound the rotor, and then slip rings. The brushes, bearings, and then you have the stator, the wire connecting box, then end shield, right. Another picture. So you will see there are some holes inside the core as well. They are actually for ventilation to cool up the core, right? And then this is the stator, this is the rotor, right? So now let's look at the operation of the induction machine. As I said earlier, the main technique that we use here is a rotating magnetic field. So rotating magnetic field concept, which was introduced by Tesla in 1882. He said when a balanced 3-phase windings uh, that is spatially spaced from each other by 120 degrees. So when we say balanced 3-phase windings, their current is having 120 degrees electrical separation. In addition to that, now we are going to keep 3 coils physically 120 degrees apart, right? And then they are supplied with 3-phase current. Then if you supply 3-phase current, we can show that rotating magnetic field is generated. That means, say for example, at this point, say sorry, let me draw it and show you. Say now at this particular instance, the magnetic field is in this direction. So that means it is like having a magnet, permanent magnet, which is having north pole in this side and south pole in this side, right? So and then these are AC currents, so their magnitude is changing. So and also they have a phase angle 128-degree phase angle difference. Therefore, this magnetic field that is created is also rotating, right? So that is the main principle that we use in induction machines. And a rotating magnetic field with constant magnitude is produced. So the magnitude of this field is constant. And the rotating speed, which is called the synchronous speed, ns, can be calculated if we know the frequency of the supply and the number of poles. So it is 120 into frequency divided by number of poles. So this equation you have to remember. By this you can calculate the synchronous speed. That means when it is stable, steady state, what is the speed of the rotor is given by this. It's called synchronous speed. So this rotating magnetic field passes through the air gap and cuts the rotor conductors, which are initially stationary. So you have to visualize now. When the rotating magnetic field is rotating, right, it is cutting the rotor coils or rotor bars, right, rotor conductors. Due to the relative speed between the stationary rotor conductors and the rotating magnetic field, an EMF is induced in the rotor conductors. Since the rotor circuit is closed, I said that from the two end caps, the rotor conductors are short circuited. The induced voltage in the rotor windings produce rotor currents. So now on the rotor bars a current will flow, right? And as these current carrying rotor conductors are placed in the magnetic field produced by the stator, they experience a torque which moves the rotor in the same direction as that of the rotating magnetic field. So then what will happen, the rotor will start to move in the direction of the rotation of the magnetic field. So due to this magnetic force or the torque generated by the external field. So this is how the induction machine rotates. This rotating magnetic field might be a new concept for you. It can be either generated in two-phase or three-phase machines. So to establish rotating magnetic field in a motor, the number of pole pairs must be same or multiples of number of phases in the applied voltage. So that means if you have only two pole pairs, then you can connect two phases. If you have three pole pairs, then you can connect it to a three-phase supply, like that, right? So the poles must be displaced by each other by an angle equal to the phase angle between the individual phases of the applied voltage. So the poles must be displaced by each other by an angle of by an angle equal to the phase angle between the individual phases of the applied voltage. So let's look at how this rotating magnetic field works. So here you can see the three phases red one, the green one and the blue one. So between these three phases electrically you know 120 phase difference is there, and each coil is forming a magnetic field, north in one side, south in the other side. But here we are going to use a convention in drawing the resultant magnetic field, because those three magnetic fields will cause one single resultant magnetic field. So in that case we assume when in the positive half cycle, when the supply voltage is positive, the direction of the field is into the coil, and when the magnetic field is negative, the when the electric current is negative, the magnetic field is outward from the coil, right? So in that case the green one and the red one both are positive at this particular instant. We are looking at the very first instant here, t equals 0. So at that point green and red, actually red one is 0, only green one is there, and then the blue color one, it is negative. So the green one, as it is positive, according to this convention, magnetic field is towards the coil, and for the blue color one, as it is negative, it is outside, towards the outside of the coil. So the direction of blue color one is this, and the red color one, it is not generating any magnetic field because the voltage is 0. So therefore we have to add only these two magnetic fields, then the resultant will be somewhere here. That is the addition of this magnetic field to this one, then you get this one resultant. So north, the effect of these two coils will generate a north towards this side and south towards this side. Okay, then if we consider another point in time and do the same thing for to calculate the magnetic field. For example, when the time is somewhere here, the green one magnitude is this one, the red one is this, and the blue color one is this. So the green and red are still positive, the blue color one is still is negative. So now if we look at the magnetic fields generated, green and red one towards the coil, green and red one towards the coil, and here the magnetic field strength is smaller as the current is smaller, and here it is a bit larger one because voltage is higher here, and then the blue color one is going outward from the coil, so it will be in this direction. So we have to add all these three together to find the resultant. So we will start with the red color one, and blue color one is added to that, and then the green color one. So we get the resultant in this direction. Earlier it was somewhere here, now it is rotated to this direction. So Then if we look at another point, where the green one is also negative, only the red one is positive, and green one and blue one are equal in magnitude. Therefore you get equal magnitude, but both are negative, therefore going outward from the coil. So the resultant will be in this direction, and it will be added to the red color one, which is positive, so it is going towards the coil, so this direction. Therefore the addition will be this one plus this one plus this one, so you get the resultant one in this direction. So earlier it was here, then it was here, now it is somewhere here. So like that you will see the resultant magnetic field is rotating in this direction when you supply these three coils with three-phase balance supply. And let's take one more instance uh, where you get blue color one is positive now, red is still positive, green one is still negative. So then according to this convention, green one is negative, so it is outward. Red one and blue one are positive, though, so they are actually inward. Red color one should be somewhere here. So the resultant will be green one plus red one plus blue one, so it will be somewhere here. So you saw that the magnetic field is rotating like this, right? So this will be very clear when you look at the video clip that I am sharing after this one. So you will be able to understand how the magnetic field is rotating when you supply these three coils with balanced three-phase supply. So then we can calculate the synchronous speed. If we know the frequency of the power supply and the number of poles, the equation is Ns equals 120 F over P. So a simple calculation can be done for this example. A three-phase two-pole induction motor, so three-phase two-pole induction motor, P equals 2, right, is connected to a 50 hertz supply, so F is 50 hertz. So if you know frequency and number of poles, you can find the synchronous speed. It will be here 3000 rounds per minute. Right. Then we would look at the slip, the term called slip. Acceleration of the rotor um, and the slip. The rotor revolving in the direction of rotating field will accelerate and eventually reach a steady state speed n that is less than the synchronous speed ns. So you will see that when the three coils are supplied with three-phase supply, uh, uh, there is a magnetic field created, and that magnetic field is rotating. So that rotating magnetic field will induce some EMF on the rotor bars. So so they are as the rotor bars are short circuited through the end plates, there will be a closed circuit and current will be flowing inside the rotor bars. So when you have current carrying conductor in a magnetic field, there will be some torque generated on the conductors. So due to this torque, the rotor start to rotate slowly. So after some time it will come to a steady state. That means rotating at a steady speed. That speed is n, which is less than the synchronous speed. I will tell you why it is less. In order to induce an EMF in the rotor must move slower than the synchronous speed, right? Otherwise, if they are rotating in the same speed, there is no relative motion. So therefore there will be no EMF generated. So if we want an EMF generated, then there should be a speed difference, because if the rotor were to turn at the synchronous speed, the EMF uh, could not be induced in the rotor and the rotor would stop. Therefore the rotor speed is always slightly less than the synchronous speed. What will happen actually, the speed of the rotor gradually increases. When it comes to the synchronous speed, then the EMF generated will be 0. Therefore the torque will be 0. Then what will happen, the rotation will be slowed down. So when the rotation speed slows down again, there will be magnetic flux cut by the conductor bars due to the speed difference. So then again EMF will be generated, and torque will be applied on the rotor and it start to rotate. So like that it is when it comes to a steady state, uh, it is running at a slower speed than the uh, synchronous speed, the rotating magnetic field speed. If the rotor slows uh, significantly, uh, if the rotor slows significantly or stops, an EMF would once again be induced in the rotor bars and it would begin rotating again at the speed less than the synchronous speed. That is what I explained. So then let's see what the slip means. The difference between the rotor speed and the synchronous speed is called the slip speed, and it is defined as n slip equals n synchronous minus uh, speed of the rotor n. This is in rounds per minute. You can do the same with radians per second. The conversion is rounds per minute value. You have to multiply by 25 and divide by 60 to find the radians per second. This you can easily remember because rounds per minute, minutes in the down, the bottom. Therefore, uh, if you want to calculate per second, then you have to multiply this by 60, and one round is 25 radians. Therefore you have to multiply top side by 25. So if you want to convert RPM into radians per second, you have to multiply it by 25 and divide by 60. So here the slip speed, this is called the slip speed, and slip is equal to the synchronous speed minus the rotor speed. Right. So that is the slip speed. Now let's look at slip. The slip speed normalized to the synchronous speed is defined as this slip. So that means the slip speed you have to divide by the synchronous speed, then what the value you get is called the slip. Therefore you can calculate the rotor speed n as 1 minus s, or 1 minus s, 1 minus slip into ns. The same thing can be done by using radians per second angular speed. Then the angular speed of the rotor will be equal to 1 minus s into synchronous angular speed of the magnetic field. If the motor speed equals the synchronous speed, if they are same, then s will be 0. And if the motor is stationary, that means n equals 0, then s will be 1. So um, for a rotating machine, induction machine, s will be lie between 0 and 1. So this ratio slip is mostly given as a percentage, right? This is a ratio, so it can be given as a percentage, say 5% slip, 10% slip, like that. So the slip speed is equal to slip into synchronous speed. That is clear, right? N slip equals s times ns. That you can actually derive from the previous. I go back. If you want to calculate n here, that is the rotor speed. Yeah, what was the value that we mentioned here? N slip. That is the slip speed, right? So slip speed is, let me go back. This is slip now. Slip speed is this one. N slip is ns minus n. So n is actually some percentage of ns. So it will be 1 minus s into ns. So here in this slide it talks about n slip, that is the slip speed, is equal to slip into synchronous speed. Yeah, here for n, if you apply this one, from this one 1 minus s into ns, if you put 1 minus s into ns here, then you get n slip equals s times ns. So that way you can calculate the slip or slip speed for the induction machine. And the frequency of the current and voltage in the rotor circuit both depend on the slip speed. So the relationship between the frequency of the current and voltage in the rotor Fr is equal to slip times the frequency of the supply. In omega terms, angular velocity omega r equals s times omega. So these equations are in particular format. N slip equals s times ns. The frequency of the rotor is, the generated EMF frequency will be slip times supplied frequency, and omega r for the current and voltage is equal to S times omega of the supply. Right. Uh, so another useful equation will be Fr equals, instead of S you can put Ns minus N over Ns time F. So you can write it as F is, we know, P over 125 120 F. Therefore Ns minus N, um, and relationship between the frequency and the synchronous speed, S, that is F over Ns. If we go back here into this slide, you will see Ns equals 120 F over P. So N F over Ns is P over 120. Therefore you can substitute that here. So F over Ns is P over 125. It's P over 120. So Fr, that is the frequency of the current and voltage in the rotor, is equal to number of poles divided by 120 into Ns minus N. That is the slip speed. So this is one calculation you can do for three-phase induction machines. If we look at this example here, it says the stator of three-phase 4-pole induction motor is connected to 50 Hz supply. The motor runs at 1455 RPM, that is the speed of the rotor, at full load. So we are asked to find the synchronous speed of the rotor of the motor. Synchronous speed is actually easy to calculate because we know Ns equals 120 F over P. If we know the F and P, we can calculate synchronous speed. So here F is 50 Hertz, P is 4 poles. Therefore we get 1500 revolutions per minute. Then the slip at full load. So to find slip, you must know rotor speed and synchronous speed. So slip is Ns minus N over Ns. Therefore you can calculate, as you all know, now synchronous speed is known. Rotor speed is given 1455. Therefore you can calculate, it becomes 3%. So this type of calculation can be done for induction machines. Then another example, the frequency of the supply to the stator of an 8-pole induction motor is 50 Hertz and the rotor frequency is 3 Hertz. Now the rotor frequency Fr is given, so we are asked to calculate the slip. So we know the relationship Fr equals Sf. Therefore we can, as we know Fr and F, we can calculate S. S will be Fr is 3 Hertz, F is 50 Hertz, so it will be 6%. Slip is 6%. And then the rotor speed. So we are asked to find the rotor speed. To calculate the rotor speed, that is the n value, right? So if we know slip, if we know synchronous speed, we can calculate rotor speed. For that we have to find synchronous speed. Synchronous speed is 120 F over P, so it becomes 750 rounds per minute. So by using that value we can calculate the speed of the rotor by using S equals ns minus n over ns. So then n will be 705 rounds per minute. So one more calculation. 208 volts, 10 horsepower, 4 pole, 60 hertz, star connected or Y connected induction motor has a full load slip of 5%. So slip is given, frequency is given, the voltage is given. So what is the synchronous speed of this motor? Synchronous speed ns equal 120 F over P. So F is given, P is given, so you can calculate the synchronous speed, no issue. What is the rotor speed of this motor at the rated load? So you are asked to calculate N, rotor speed. So in this case, rotor speed, if you know the synchronous speed and the slip, then a full load slip is given. Therefore, by using n equals 1 minus s into ns, you can easily calculate the rotor speed. And then you are asked to calculate the rotor frequency. It is again easy, Fr equals Sf. So it becomes 3 hertz. So there are two ways that you can calculate Fr. So sometimes in some calculations additional information is given which is not really required, like 10 horsepower, 208 volt is not used anywhere in these calculations. Then we can find the induced EMF value as well in the rotor. The instantaneous value of the induced voltage in an N turns coil is given by, it is actually proportionate to rate of change of flux and also the number of turns. So E equals minus N d phi over dt, that is coming from the Faraday's law. So the flux is again sinusoidal, therefore we can assume it as phi m sin omega t. So if we substitute it then in this equation, E equals a minus n d phi by dt is we have to differentiate this by t, then you get phi m omega sin omega, sorry, phi m omega m, sorry, phi m omega so omega is here, phi m is here, sin differentiation is cos omega t. And if you want to express this in sine, you can write it as sin omega t minus 90, and then this minus will also go off. So the induced EMF will be n into 2 phi f phi m sin omega t minus 90. So the induced EMF will depend on the number of turns, the frequency of the supply, and the angular frequency of the supply. So these both are interrelated. Right. So the total magnetic flux in the air gap between the stator and the rotor will depend on the number of poles. However, since the windings in each pole are connected in parallel and therefore produce the same voltage, the total magnetic flux needed in the induced voltage equation is the total magnetic flux per pole. So we can write the same equation, RMS value, and then put the RMS value, then it will be 4.44 number of turns in series per phase into F, the frequency of the supply, into 5P is the flux per pole. So this equation you can remember for calculations directly. You don't have to derive it. So there are additional geometric factors associated with the arrangement of the windings that also affect the induced voltages, and these effects are taken into account in the equation by including winding factor, which is called Kw. So then the final equation for ERMS induced in the rotor is given as 4.44 turns per phase into frequency into flux per pole into a winding factor. Then modes of operation of induction motors, induction machines. There are three modes of operation for a induction machine. These modes are defined by specific ranges of slip and speed. So if it is operating as a motor, this is the natural mode of operation. That means when you supply the field coils with the current, it naturally rotates, and and the slip is a value between 0 and 1, and the speed of the rotor is less than the synchronous speed. And if it is operating as a generator, then in that case the induction machine may be operated as a generator if the stator is connected to constant frequency voltage source and the rotor is then driven above the synchronous speed by some external source. Then the slip will be minus value and the speed of the rotor will be greater than the synchronous speed. Then it is working as a generator. And the last mode is operation as a brake. So if the leads on the stator windings are reversed, the direction of rotation for the stator field is reversed. The resulting slip is larger than 1. Therefore, the motor will come to stop. The motor is then disconnected from the voltage source before it starts to rotate in the reverse direction. So this method of braking is commonly referred to as plugging. So in that case, S is greater than 1 and N is in the opposite direction less than 0. So with this I finished the introduction to induction machines. Thank you.